we already saw how to calculate the distribution of our function of our random variable. So now let me present the formal definition or an algorithm to calculate the derived distribution of a transformation of our random variable or a function of our random variable. So to calculate the PDF of a function, let's say y equal to a g function of the random variable x, we have to first, at the zero step, state the supers of x and of y. So a superplot can be helpful. Next, we have to calculate the CDF f of y of the new random variable, and that is we have to replace here the y by the function of the random variable x, that is g of x, and calculate the integral of over that new space. And finally, we have to differentiate that CDF, the CDF, to obtain the PDF. Okay, let's see another example. So consider x being uniformly distributed in the interval -1 to 1, and we have to find the PDF of the random variable y, that is the square of the random variable x. So first, let's see, our zero step is to state the supers of the random variable. So we have that x is uniformly distributed between -1 and 1. So that means x is between -1 and 1. And if we take the square of x, then y is going to be between 0 and 1, right? We can do a super plot to see this. So again, as we did in the first example of the first part of this lesson, it was something like this. In this case, we have the x random variable at the y, and we have that x is between -1 and 1, so it's between -1 and 1. And we have the function, the transformation, that is y equal to x squared. So we have that function. So that means our y variable is going to be between those values for x between -1 and 1. So we have this case again, and we have two other cases where y is not defined. So here we have one case when y is greater than 1, right? And we have another case when y is less than 0, in which also is not defined, but we have to consider it. Okay, so with that we can see that the super is between 0 and 1. That is the super where the function is defined. The other two are not defined, this one and this one, but we just keep that in mind. And the first step is to calculate the CDF of the new random variable. So that is the CDF of y evaluated in a particular value y. That is the probability that the random variable y is less or equal than lowercase of y. And we replace the y random variable using the transformation or using the function. So that is probability of x squared less or equal than y. And here we have to isolate the random variable x, so we can take a square root in both sides of the inequality. So that is the square root of x squared less or equal than square root of y. So here we know that this is the absolute value of the random variable x less or equal than the square root of y. And by definition of their absolute value, this is the same to have x between minus square root of y and square root of y, right? So if we want to see it, remember that this is y. So if we have y over here, let's say we have y over here, and we want to know what is the probability that y is less or equal than y, so we have two cases, for example here and here. So that is the probability that y is between minus the square root of y and square root of y, right? So we have to calculate this probability, and now we can use the distribution of y, the distribution of x, sorry, that is uniform. So this distribution, this probability here is the integral between minus square root of y to the square root of y of the PDF of x as the PDF of a uniform distribution between -1 and 1, that is 1 over 2 dx. So remember that this 1 over 2 is comes from the PDF of x, and this integral is the square root of y, and this probability, this function, is for y between 0 and 1. So again, if we want to define the CDF properly for all the values of y, so it's going to be 0 if y is less than 0, because it's not defined, there is no probability. We have that is this function, square root of y, if y is between 0 and 1, and we have that is 1 if y is greater than 1, right? And that's it. So we already defined the CDF, and the last step is to differentiate to obtain the PDF. So let's do it over here. Let's say our last step, step 2. The PDF is just the derivative of the CDF, so we have to differentiate it, and in this case is 1 over 2 y to the minus 1 over 2. This is for 0 and 1, and 0 in either case. If we define this for 0 and 1, that means that it's equal to 0 otherwise, right? And that is the PDF of y. Now let's consider another example. Let x to be exponentially distributed with parameter lambda equal to 1. And we have to find the CDF of this transformation of x, that is y equal to the absolute value of x minus 2. So the first step is to find the super of the two random variables. We know that x is exponentially distributed, so that is x is going to be greater or equal than 0. And to find the super of y, I think it's easier to do the super plot. So to find the super of y, we know that we have this transformation. We have x, y, we have 1, 2, 2. We know that this function y equal to the absolute value of x minus 2 looks like this, right? So to find the super of y, we have 3 cases again. This case in which y is not defined, so we have to consider it. We have another case when y is between these values, so y is between these two lines. So we have the case when y is between 0 and 2, and we have another case when y is between 0 and this line. Okay, so we know that from that y is greater or equal than 0. Doesn't matter which case, I mean these two cases, y is greater or equal than 0. That is the support. Now to find the CDF, we have to use the formula. So the CDF of y is the probability that the random variable y is less or equal than this particular value y, and we can use the transformation or the function that is in this case is the absolute value of x minus 2 less or equal than y. We now use the definition of absolute value, so that is the probability that minus y less or equal than x minus 2 without the absolute values, x minus 2 less or equal than y. And we do some algebra to isolate the x variable, so this is the probability that 2 minus y is less or equal than x less or equal than 2 plus y, right? Okay, now we have to find this probability, but we have to keep in mind that there are two cases for this y, so we have to be careful with that. To do this calculation, I think it's better to plot also the PDF of the original random variable, in this case x. So we are going to plot the CDF of this exponential random variable. Remember that the PDF, sorry, is lambda exponential of minus lambda x for x greater or equal than 0. In this case, lambda is equal to 1. So this PDF looks like this, something like this. Oh, I think this is it's something like this. Yeah, better. Okay, now to find this probability, we have to be careful because this 2 minus y could be negative, right? And we know that the x random variable is just for positive values. So let's first consider the case in which this 2 minus y is less than 0, right? So let's consider 2 minus y is less than 0, and this 2 plus y is always greater than 0 because y is greater or equal than 0. So this 2 plus y is always greater than 0. So we have this case. Let's consider this case first. So how do we calculate this probability? Well, if 2 minus y is less than 0, that means we have 2 minus y located over here, less than 0, and we have 2 plus y located over here. So if we want to calculate the probability, that is to find this area over here. So we don't do the integral from 2 minus y, but we do the integral from 0, right? From 0 until 2 plus y. So this probability is going to be, well, the CDF, remember that is 0 if it's less or equal than the first value, that in this case is 0. So it's 0 if y is not defined, that is if y is less than 0. And this and also if we have 2 minus y less than 0, that is y greater than 2, right? If y is greater than 2, we have this probability. So this probability is not calculated from 2 minus y, but it's from 0. Let's do it in this color better. I think is from 0 to 2 plus y of the PDF of x, that is exponential of minus x dx, right? And we have another case, that is, what if 2 minus y is actually greater than 0 and 2 plus y is also greater than 0? So in that case, 2 minus y is located, let's say, over here, and 2 plus y is, let's say, in the same place. 2 plus y is also here. So we have to calculate this integral. But now this 2 plus y is already defined, it's greater than 0. So to find this probability, it's going to be the integral from 2 minus y until 2 plus y of the PDF exponential of minus x dx, right? In this case is if this 2 minus y greater than 0, that means y is less than 2, but also y is greater than 0, we know that, so is y between 0 and 2. So is this value if y is between 0 and 2. Okay, you can put the equality here, doesn't matter. So finally the CDF is 0 if y is less than 0. It's going to be this integral if y is between 0 and 2. If we evaluate that, is exponential of y minus 2 minus exponential of minus y minus 2 if y is between 0 and 2, and it's going to be this integral if y is greater than 2, so it's 1 minus exponential of minus y minus 2 if y is greater than 2, right? So this is the value for this one, and this is the value for this one, and that is the CDF.